Good morning, kids. We're going to be working on our first lesson today on our Ksp solubility unit. We're going to be following the same basic math that we used in the equilibrium unit, but we're going to be applying this specifically to dissolving solids into liquids. Before we can do that, I want to review our grade 11 solubility unit. I know for several of us it's been a while since we have covered it. So from the beginning of our notes set, if you follow along with me, I'll be adding notes just like I would in class, and I encourage you to add notes and work along within your own workbooks. So we have a bunch of terms that we need to remember, and I have them here in blue and bold print so that they stand out for you. These are the words that you're going to be responsible to understand in the unit. Anytime we make a solution, we have to have two components. We have to have a solute and a solvent. Now, these systems actually can be either reversible or irreversible. Think, for example, of a cup of coffee. If I put some sugar in a cup of coffee and just stir it up and it dissolves, that's irreversible. The sugar just dissolves and it just goes away. You're not going to see it anymore. However, if I continue to add sugar to the solution, I'm going to get a point where no more sugar is going to dissolve, and then I'm going to call that solution saturated. It's holding as much as it can hold. It can't hold anymore. At this point, our solution is said to be in a state of dynamic equilibrium. It's not that the dissolving process has stopped. What we really have happening here is that every time one sugar molecule that is down here in the solid phase, in the bottom of the cup, every time one of those solid pieces of sugar dissolves up into the solution, now I'm going to have it in the aqueous phase. It's dissolved. I will have at the same time another one that will recrystallize and go down back into the solid phase. So we will have sugar going from solid to aqueous and from aqueous back down to solid. There's our equilibrium. We're going to have an equilibrium from undissolved to dissolved. So this is when we can have an equilibrium situation, and we can often call this dynamic equilibrium because the reaction continues. It doesn't stop. That's important to remember because it's a problem that a lot of kids have with these. Now, another word that we talked about in the past was solubility. Solubility is that maximum amount that can stay dissolved. It's going to depend on things like how much liquid do we have and how soluble the different salt is. It also depends very much on temperature, and if we're dissolving a gas into a liquid, it would also depend on pressure. Solubility is usually measured in units of grams per liter, or we might have it measured in units of moles per liter. This is going to be the one that we're going to use in our equilibrium calculations, moles per liter. Remember, there's a shorthand for that. It's this symbol here, mu, which stands for molar. And the symbol molar, this looks like a handwritten M, it's actually the Greek letter mu, actually hides two numbers and two units. Basically, it's telling us that we're going to have 1 mole of substance dissolved in every 1 liters, or whatever amount of moles it could be. We could just say there's going to be X moles of substance in every 1 liter. So we have to remember that every substance has a unique solubility, a maximum amount that can dissolve. Now there's 3 things that are going to affect what that maximum amount is. The first one is the nature of our solute and solvent. We've got that whole concept of like dissolves like that we talked about in grade 11. If I have a polar solute, something that has a positive and a negative looking end, it will dissolve readily in a polar solvent, very much like water. If I have a nonpolar solute, it would need a nonpolar solvent in order to be able to dissolve. Okay. So that is the first one that we have to remember in the idea of like dissolves like. The second thing that's going to determine our solubility is the temperature. If we're dissolving a solid, we know from experience we can dissolve a lot more solid in a liquid if it's at a warm temperature than we can if it is at a cool temperature. I can dissolve a lot more sugar in a hot coffee than I can a cold coffee. Gases, however, is the opposite. When we have a liquid heat up, the molecules of water, for example, in a gas will spread apart. So if I just draw my little cheater molecules here, we can think about water as an L-shaped molecule with an O and two H's. There's one water molecule. I'm going to draw another couple just as an L-shaped molecule because it's a little easier for me to draw on my computer screen. What happens when we heat water up and I have a gas trying to be dissolved? Remember, to be dissolved, you have to be held in a little cage of water molecules. Well, what's going to happen in this scenario is the water molecules are going to spread apart. And once the water molecules spread apart, that gas, who was highly active and had lots of energy, will escape. And we will be able to dissolve less. Solids, when they were dissolving in the water, oops, sorry about that, the solids, as they were dissolving in the water, they can't move very fast. So what happens when we spread the water molecules out like this is we actually have more room to dissolve more solids in the same amount of space, because as they're sitting there, solids move so slow that if they try to escape from that little water cage that's holding them all together, they can't do that. Now, that water cage has a name. From grade 11, we call that a hydration shell. I'll give you that spelling, hydration shell. I apologize for my messy writing. I am trying to write with a little pen on a laptop screen. So we've got our first two things that are going to affect our solubility. The last one that's going to affect the solubility is pressure, and pressure is only going to be a factor if we're trying to dissolve a gas into a liquid. It has no effect if we're trying to dissolve solids or liquids. The only thing that can be affected by pressure is gases. Now, there is a law called Hess's law that talks about the solubility of gases and into liquids, and it basically says that if I double the pressure, I can dissolve twice as much. If I triple it, I can dissolve 3 times as much. They will talk about it in your textbook. And it seems silly that they don't force you to learn it because it is very, very simple math, but art specifically says in our curriculum guide that that's not to be taught. So I'm going to refer to it here that we just know if we have more pressure, we can dissolve more. And that's about as far as we have to go with that at the grade 12 level. So what I'm going to get you guys to do for this first lesson is actually go, first of all, to the workbook section of your package. Now, if you go to the very back part of your package, which seems very thick for this unit, you're going to find a bunch of sheets that look like they were photocopied out of a textbook. They've actually been photocopied out of the correspondence course for the province of Manitoba. Look at the page numbers up at the top. I want you to find the pages numbered 175 to 182. These will be in your blue workbooks. And the title on them is Solubility Lesson 1. What you're going to notice as you start reading through those pages, starting at 175, is that there is notes given to you. And along the side, in the margin, they have a key and then a list of terms. These are the key terms. They are the words that you're responsible for. If you were sitting in my classroom right now, I'd be telling you I want you to write out a definition for each of those terms. What I'm hoping you're going to do now is make sure that if I ever ask you what do these words mean on an assignment or a test, that you can give me even a plain words understanding of what those terms mean, because we'll be using them throughout the unit. Then, as you continue to flip through the readings, you'll find a short series of questions. One of them will be on the page numbered 179, and the next one the page numbered 182. And you will see that those questions are based on exactly what you just read. So they're there to see if you understand the basics of it. We will also get you guys to read in the textbook chapter 14.3, pages 49 to 496. And I would traditionally have you guys do this as an independent reading, and I would go over the answers with you guys next class. I'm going to be looking for a set of questions for you in the chat section of our online teams here. I'd prefer we did them in the chat so everybody gets to benefit from any of the answers that I share. And I would like you guys for your first lesson to try and see if you can get through just that little section. So again, this workbook section here that I'm circling is in our blue work booklets, okay? The reason the page numbers are there is because I photocopied it from the government curriculum guide. This part up at the top is from your textbook. So this is our first lesson. Good luck with it. I'm looking forward to seeing your comments in the chat page. Thank you guys very much, and we will be talking to you soon.